Now we are familiar with kets, bras, inner products, operators, the action of operators, the Hermitian conjugate of an operator, the concept of Hermitian operator, right? So we are familiar with the basic mathematical formalism. The next section is on base kets and matrix representations. We start with eigenkets of an observable. By observable, of course, we mean an operator representing the observable. So we'll discuss the eigenvalues and eigenkets of an observable, reality of eigenvalues of Hermitian operators. So we'll see that if the operators are Hermitian, their eigenvalues will be always real. This is something that we have mentioned several times. Now we'll set out to prove it. We'll also see that the eigenkets of Hermitian operators corresponding to different eigenvalues are actually orthogonal. Right? So when we say orthogonal, it means that the inner product is 0. So let's look at these things. Let us start by considering the eigenkets and eigenvalues of a Hermitian operator A. Right? So we are starting with the Hermitian operators because Hermitian operators are important to quantum mechanics. We will see that physical observables are actually represented by Hermitian operators. So we begin by stating an important theorem. This theorem is fundamental to quantum mechanics. So let's look at it. The theorem says that the eigenvalues of a Hermitian operator A are real. The eigenkets of A corresponding to different eigenvalues are orthogonal. Okay. Now there are two parts to this theorem. It says that if the operator is Hermitian, the first part of the theorem says that if the operator is Hermitian, then its eigenvalues are always real. The second part says that the eigenkets of A corresponding to different eigenvalues are orthogonal. So we have to prove both these parts. The proof goes like this. We start by writing the eigenvalue equation. So this says that A acting on ket A prime is equal to A prime multiplied by ket A prime. Okay, so this is the definition for an eigenvalue equation. The operator acting on the ket does not change the direction of the vector, but merely multiplies it by a number. Okay, now this number is called the eigenvalue, and this vector is called the eigenvector. Okay. Remember, this is a number and this is a vector. This is called the eigenvector or eigenket. We'll call it as eigenket. We'll be using all these words interchangeably. Eigenket, eigenvector, eigenstate. Okay, all these words will be used interchangeably because in our context they all mean the same thing. Okay, now this here we are using the notation that we are using the eigenvalues to label the kets. The eigenkets are labeled by the eigenvalues. We can say ket A prime is the eigenvector corresponding to the eigenvalue A prime of operator A. Okay, so we are labeling kets by the eigenvalue of operator A. All right. Now you could write another eigenvalue equation with a different eigenvalue A prime, A double prime. Okay, here A double prime is the eigenvalue of operator A. Okay, or ket A double prime is the eigenket of operator A corresponding to the eigenvalue A double prime. All right. Now this is the eigenvalue equation for the ket. We can also have corresponding eigenbras. Okay, so let's look at the corresponding eigenbras. Let's take the dual correspondence. The dual correspondence of the left-hand side is that bra A double prime A dagger. Okay, this was the definition. This was the definition for the operation dagger or Hermitian conjugate. So the dual correspondence to this equation becomes, or the corresponding bra equation becomes, bra A double prime A dagger is equal to bra A double prime and then A double prime star. Okay, this number in general is complex. So when you take the corresponding ket, when you go to the corresponding ket space, it becomes a complex conjugate. Okay, this rule we have already seen. An operator, when it goes to the ket space, it becomes the Hermitian conjugate. A number becomes a complex conjugate. Okay. All right. Now we have said that A dagger. So we have said that A is a Hermitian operator. A is a Hermitian operator means A is equal to A dagger. Okay. So since A is Hermitian, this is the definition for a Hermitian operator. Since A is Hermitian, this equation for the eigenket, so the eigenbra can be written as bra A double prime A, or operator A acting on bra A double prime is equal to A double prime star bra A double prime. Okay. Now we have got two equations. One which involves the eigenket and another which involves the eigen bra. Okay. Now this will call equation 1 and this will call equation 2. So this is equation 2. Bra A double prime A is equal to A double prime star bra A double prime. This is equation 2. Equation 1 was this: A acting on get A prime is equal to A prime multiplied by get A prime. This is equation 1. Alright. Now what we do is we take equation 1 and you push a bra A double prime from the left. Okay, so we are just multiplying a bra A double prime from left. Okay, so this left hand side becomes bra A double prime A get A prime is equal to bra A double prime A prime get A prime. Okay, now this is a number, this is an eigenvalue, so it doesn't matter whether you put the number on the right or on the left of the get or the bra. So we can just pull this number out. So we get this equation as A double prime A prime is equal to A prime A double prime A prime. Okay, let's write this as equation 3, or let's say 1a. Let's write this as 1a. Okay, now we take equation 2. We take equation 2 and then what do you say, multiply by a get A prime on the right. Okay, just introducing a get A prime on the right of this equation. So you take equation 2 and introduce a get A prime on the right. So this becomes bra A double prime A get A prime. I've introduced a get A prime here. This is equal to A double prime star from here, bra A double prime, and then I have introduced this A prime here. Okay, this I can write as 2a. Right? Now you see that we have got two equations whose left hand sides are equal. The left hand sides are equal. Okay? Now we can subtract one from the other. So let's subtract the second 2a from 1a. Alright, so 1a minus 2a becomes, you get left hand side is 0, and here you see that this bracket of A double prime A prime, it's the same here also, bracket of A double prime with A prime. Okay, so the left hand side becomes 0. We get 0 equal to A prime minus A double prime star. Okay, now I am pulling this bracket of A double prime A prime out. So this becomes bracket A double prime A prime. Now we have the result. That's how we get this equation. A prime minus A double prime star multiplied by bracket A double prime A prime is equal to 0. Okay. Now A prime and A double prime can be taken to be either the same or different. Okay, so we didn't say anything about A prime or A double prime. There are two cases that we can think about. Okay, A prime and A double prime could be the same or they could be different. Okay. So let's write the equation here. The equation that we got was A prime minus A double prime star. Okay, and then bracket A double prime A prime was equal to 0. Okay, I think this is what we had here. Is A prime minus A double prime star multiplied by bracket A double prime A prime is equal to 0. Okay, this was our equation 3. Now we said that there can be two cases. The first case is that these eigenvalues could be the same. So let's first choose them to be the same. Let's choose the eigenvalues to be the same. Okay, we then deduce the reality condition that A prime has to be equal to A prime star. Alright, so this means that I'm taking these eigenvalues to be equal. Okay, so this equation becomes A prime minus A prime star, then bracket A prime is equal to 0. Equation, if these eigenvalues are real, we get this equation. Okay, now this is the inner product of a vector with itself, which cannot be 0. Okay, this we have already seen. We started with a positive definite metric. So unless get A prime is a null vector, we know that this is positive definite. So this cannot be 0. It's inner product of a vector with itself, and we are not talking about null vectors. All right, if you are talking about null vectors, then we don't get any result. That's a trivial case. So if this is any vector that's not a null vector, this cannot be equal to 0. This means that A prime minus A prime star has to be equal to 0 for this equation to be satisfied. Okay. Now this means that A prime is equal to A prime star. A prime equal to A prime star means A prime is a number which is equal to its own complex conjugate. Alright. Now this is generally true. This is generally true for any A prime and A prime star. This means that this is a real number. This means that this is a real number. So for a real number, the complex conjugate of a real number is the same, right? It doesn't change. So we have used the fact that ket A prime is not a null ket. Alright, so we have got this result that the eigenvalues of a Hermitian operator are real. Right, the eigenvalues of a Hermitian operator are real. So we have actually proved the first part of the theorem. We proved the first part of the theorem. The eigenvalues of a Hermitian operator are real. Okay, or A prime is equal to A prime star. So in order to prove the second part of the theorem, let's take A prime and A double prime to be different. Let's take A prime and A double prime to be different. All right. So, but in view of the reality of eigenvalues, we have the first part we have already proved. So this means that this equation, the eigenvalues are real, right? So this equation can now be written as A prime minus A double prime, because A double prime star has to be equal to A double prime. The eigenvalues are real, as we just proved. Okay. So A prime minus A double prime bracket A double prime A prime is equal to 0. Alright. Now let's take the case where these are different. If A prime and A double prime are different eigenvalues, they are not equal, then this cannot be equal to 0. This cannot be equal to 0. That means that bracket A double prime A prime is equal to 0. In other words, the eigenvector corresponding to different eigenvalues of a Hermitian operator are orthogonal. Right? If the inner product between two vectors are 0, if the inner product between two vectors is 0, we say that these two vectors are orthogonal. Right? This is the orthogonality condition. This means that these are orthogonal. All right. So because of the just proved reality condition, the difference A prime minus A double prime star that appears in this equation is equal to A prime minus A double prime. Okay, I'm just repeating what I did here, which cannot vanish by assumption. Right? What was the assumption? The assumption that we are talking about different eigenvalues. So this cannot vanish. The inner product bracket A double prime A prime must then vanish. Okay, so bracket A double prime A prime is equal to 0 if A prime is not equal to A double prime, which proves the orthogonality property. This was the second part of the theorem. The second part of the theorem said that the eigenvectors corresponding to different eigenvalues of a Hermitian operator are orthogonal. These are orthogonal. Okay. Now we expect on physical grounds that an observable has real eigenvalues. Why is this? Because we already said, I think we have already mentioned that observables are represented by operators. Okay. And we said that the possible measurement outcomes, we just write it shortly, possible measurement outcomes are the eigenvalues of the operators. Right? But the possible measurement outcomes of an observable are always real numbers. Okay? If you measure something, you never get a complex number. You always get a real number. If you measure the speed of a particle, or if you measure the voltage or the current, all these are real numbers. Right? So the eigenvalues, the observables, right, the measurement outcomes of observable must be real. Right? This means that the eigenvalues of the operators that we choose must also be real. Only then this mathematically, only then this scheme will work. Right? So it's important for our scheme to work that the observable has real eigenvalues. Right? This means that we cannot choose any operator to represent an observable. We can only choose those operators whose eigenvalues are real. We can only choose those operators whose eigenvalues are real. Okay, and such operators are actually Hermitian operators. This means that we have to say that observables are represented by Hermitian operators. Okay, not any operator, but by Hermitian operators. That's why we talk about Hermitian operators in quantum mechanics. Now we can find a normalized set, an orthonormal set. What do we mean by an orthonormal set? Okay, so it's conventional to normalize ket A prime so that the set of eigenvectors form an orthonormal set. What do we mean by an orthonormal set? So let's start with the usual Euclidean case. In the Euclidean three-dimensional space, we have got three. We usually talk about three unit vectors: x hat, y hat, and z hat. Okay, or we say more commonly, I think we write as I hat, j hat, k hat. Okay, these are the unit vectors along the three coordinate axes, three Cartesian coordinate axes. Okay, this is actually an orthonormal set. It's an orthonormal set because x dot y is equal to 0, okay, and x dot z is equal to 0, and y dot z equal to 0. Right? This means that they are all mutually orthogonal. Right? So this is an orthonormal set because they are mutually orthogonal. That's not the only thing. They are also normalized to 1. X dot x equal to 1. These are all unit vectors. Okay, these are all unit vectors. Okay, so in this case we say that this is an orthonormal set. In the same way, we can talk about an orthonormal set of eigenvectors. Right? In other words, we can take the eigenvectors and normalize them, and then we'll have an orthonormal set. Okay? So the orthogonality means that a prime with a double prime. Okay, bracket. We say that, for example, we have already seen this definition. Ket a prime and ket a double prime are orthogonal if bracket of a prime with a double prime, or this is also equal to bracket of a double prime with a prime, and this have to be equal to 0. So two vectors are orthogonal if this condition is satisfied. Okay, now if this is true for any pair of vectors, in the set, they are all mutually orthogonal. Okay, now this we have already seen, the different eigenvectors are actually orthogonal. So the first part is fine. So in order to make it orthonormal, we need to have this condition, right? We need to have something like this condition, x hat dot x hat equal to 1. In other words, we need to have this as unit vectors. How do we make sure that these are unit vectors? By again demanding that these are equal to 1, etc. This means that the inner product, right, the inner product is 1 if they are the same vector. The inner product is 0 if these are different vectors. Okay, in general, we can write this as bracket a double prime a prime is equal to 1 if a double prime and a prime are equal, is equal to 0 if a double prime is not equal to a prime. Okay, so in general, we can write this as delta a double prime a prime, where delta is the Kronecker delta. So Kronecker delta says that this is equal to 1 if a double prime is equal to a prime. This is equal to 0 if a double prime is not equal to a prime. Okay, so if we normalize these kits, we'll say that we have an orthonormal set. All right. Now, what's the specialty of this orthonormal set? They form a basis. Okay, they form a basis or a set of base vectors. They form a basis or a set of base vectors. Okay, what's the importance of the set of base vectors? Any vector in the three-dimensional Euclidean space can be written as a combination of these base vectors, right? For example, we can write a vector is equal to ax plus ay hat plus az z hat. These are called components. Ax, ay, az are components of the vector along the directions x hat, y hat, and z hat. Okay. So we know that this forms a basis, right? We can also ask the same thing here. It sounds so similar, so we can ask the same question here. Does this set form a basis? All right. Does this set also form a set of base vectors? All right. Or in other words, does this set of eigenvectors, does this set of orthonormal eigenvectors form a basis? Okay. The answer is yes. So the question is this set of eigenkets complete? When do we say that a set of vectors is a complete set? So let's try to answer this question first. When do we say that a set of vectors is complete? Okay, we can say a set of vectors is a complete set if two conditions are satisfied. One is that the number of vectors in the set, has to be equal to the dimensionality of the space, to all these vectors must be independent. Okay, now again we can go back to the example of the three-dimensional Euclidean space, and this thing becomes clear. We have this base set x, y, z. All right, how many vectors are there in this set? There are 3 vectors. Okay, What's the dimensionality of three-dimensional Euclidean space? It is 3. So you see that in this set there are 3 vectors. So the number of vectors in this set is equal to the dimensionality of the space. Right? The next condition is that all these vectors must be independent. Right? All these vectors must be independent. That's also true here. And in this case, the independence is guaranteed because of the orthogonality. Okay? Since x hat dot y equal to 0, y dot z equal to 0, right? And z dot x equal to 0. This means that they are mutually orthogonal. If they are orthogonal, if they are mutually orthogonal, they are also independent. Okay. So one way to understand that this is independent is you cannot write x hat in terms of y hat and z hat. Alright. If you are able to write x hat in terms of y hat and z hat, then they wouldn't be independent. So these are 3 independent directions in the 3-dimensional Euclidean space. Okay. Now orthogonality guarantees that these are independent. Right? So if this x hat dot y hat is 0, means that x hat has no component along y direction, x hat has no component along z direction. Okay. Similarly, y hat has no component along x direction and y hat has no component along z direction. That's the case also for z hat. This means that x hat cannot be expanded in terms of y and z, y hat cannot be expanded in terms of x and z, etc. All right. Now we can ask the same question. I think the idea of complete set is somewhat clear. We can ask the same question in the case of eigenkets. Is the set of eigenkets complete? All right. So let's check this. Is this set a complete set? The first condition is that the number of vectors in the set has to be equal to the dimensionality of the space. All right. Now this is actually true by construction. This is exactly how we have constructed our vector space. Right? We said that the dimensionality, I think in one of the previous classes we discussed the dimensionality of the vector space we were constructing, and we saw that the dimensionality is equal to the dimensionality of the vector space is equal to the number of eigenvalues. And corresponding to each eigenvalue, there's an eigenvector. So number of eigenvalues is equal to a number of eigenvectors. Okay. Now the dimensionality was equal to a number of eigenvalues. That means that the dimensionality is equal to a number of eigenvectors. All right. So this set has a number of vectors which is equal to the dimensionality of the space. Okay. This is true by construction. This is how we constructed our vector space. Right. Now, are they orthogonal? Yes, they are orthogonal. Right. Or are they independent? Right. They are independent, and this independence is guaranteed by the orthogonality. We already saw that this condition is also satisfied. This is orthogonality. Right. So these two conditions are satisfied. The number of vectors in this set, the number of kets in this set is equal to dimensionality of the space. This is true by construction. This is how we started constructing our vector space, right? We wanted to describe the Stern-Gerlach experiment, and we said that we have to construct a vector space whose dimensionality is equal to the number of eigenvalues of the operator. Okay, so dimensionality is fine, and all these vectors are also independent. This is guaranteed by the orthogonality. We have already shown that these eigenvectors corresponding to different eigenvalues are orthogonal. Okay. So the answer here is that this set actually forms a complete set. This set of eigenkets of a Hermitian operator actually forms a complete set. This means that any vector, any ket in this space can be expanded as a linear combination of these eigenkets. All right. So since we started our discussion by asserting that the whole ket space is spanned by the eigenkets of A, right? So we were talking about the span of the eigenkets of A. So the vector space that we constructed was the span of the eigenkets of operator A. The eigenkets of A must therefore form a complete set by construction of our ket space. All right. So it forms a complete set. Now let's conclude by summarizing what we have seen so far. We talked about Hermitian operators. Hermitian operators are those operators which satisfy this condition: A dagger is equal to A. If you take the Hermitian conjugate, it does not change anything about this operator. Alright. Now we saw that these Hermitian operators have some very useful properties. We saw that the eigenvalues are real. We proved that the eigenvalues, we proved the theorem which says that the eigenvalues of a Hermitian operator are real. This means that we can choose Hermitian operators to represent observables. Okay, and the measurement outcomes will be related, then can be equated with the eigenvalues. The second was that the eigenvectors corresponding to different eigenvalues are orthogonal. The eigenvectors are orthogonal if they correspond to different eigenvalues. Okay, or we said we call them as eigenkets. The eigenkets corresponding to different eigenvalues are orthogonal. Okay, all right, and we said that we can use this. Okay, we said that it also forms a complete set. Okay, we said that the set of eigenvectors forms a complete set. This means that we can expand any vector as a linear combination of these eigenkets, right? In other words, we can say that the set of eigenkets forms a basis. Okay. Now we can come back to the analogy with the three-dimensional Euclidean space, which we are familiar with. Or let's take the two-dimensional Euclidean space, this plane. Okay, we could take these two directions as the unit vectors. But the choice of unit vectors is not unique, right? We can take another set of we choose orthogonal vectors for convenience. We could choose another set of vectors, x hat prime and y hat prime. This also will form a basis. So if you have a vector in this space, you can either expand it in terms of x hat and y hat, or you can expand it in terms of x hat prime and y hat prime. Okay, or you could choose another set of basis vectors, x hat double prime and y hat double prime, etc. So what I am saying is that the choice of base vectors is not unique. We are familiar with this property from the study of three-dimensional or two-dimensional Euclidean spaces. Okay, the choice of base is not unique. Okay, that's also the case here. We have chosen the eigenvectors or eigenkets of a Hermitian operators as base vectors. All right. Again, coming back to this three-dimensional Euclidean set, let's take three-dimensional Euclidean or two-dimensional Euclidean space. Sorry, let's talk about the two-dimensional Euclidean space, and let's consider these two separate sets of base vectors. This is x hat and y hat, and this is x prime hat and x hat prime and y hat prime. Okay, these are two different sets of unit vectors. Sorry, these are two different sets of base vectors. All right, and we know that we can go from one set to the other by making a rotation. Right, by having a rotation, we can go from one set to the other. So these two sets are related by a rotation. Right? Now, in the same way, we'll see, right, this is something interesting, we'll see that this base is also not unique. Right? This basis is not unique. Which means that we can construct other basis vectors also. Okay? How do we construct other basis vectors? In quantum mechanics, we know that there are different observables. All right? We talked only about one observable A. Now, suppose there's another observable B. B will be a Hermitian operator because we said that we'll represent observables by Hermitian operators. All right? And the eigenvectors of B also will form a complete set or a base set. Okay, or a set of basis vectors or set of base vectors. Right? Now we have, once we identify two operators A and B, we'll come to the details of this. Okay, what's the condition, etc. But for now, if there are two operators A and B, then we have got at least, okay, we are interested in two different set of base vectors. And there are transformations which will take us from one basis to other basis, etc. All these things we'll be discussing later on. Right? So this is just again to give you a hint of what are the kinds of things that we are going to see. So in this case, just as there are rotations that connect these two base sets, okay, here also there are transformations that connect these two bases. Okay. So these are the things that we'll be discussing later on. We'll stop with that now. Thank you.